25 plus 5. Right? So our next speaker is Joe Conlon. He will tell us about exploring the holographic swampland. Please take it away.
Thank you very much, Gary, and thank you for the invitation. So this talk is about applying kind of holographic ideas for the swampland, and it's based on work that mostly that is being done over the last few years with myself and Fernando Quevedo, and with myself and my student Filippo Rivello, both as a paper from last year and a paper from this year, also with my student Siri Ning. So Filippo is applying for postdocs, and I thoroughly recommend him. He's very good. So please look out for his application. Okay, so I just want to start with maybe like the philosophy of what we're trying to do. Okay, and so this is a view that I do definitely believe in, although I have absolutely no evidence for it. Okay, so when we want to get to the real world in string theory, we don't want to describe imaginary worlds, we want to describe the real world. And so the natural vacua, when you do moduli stabilization, given the audience, I'm not going to justify moduli stabilization or say what moduli are. I'm just going to go straight into this. So when you do moduli stabilization, the natural vacua are often ADS vacua. And in some ways, the sort of standard thing to do is to say, well, we have an ADS vacuum, and then we somehow fiddle with it to turn it to a de Sitter vacuum. So you put an anti-D3 brain down a warp throat, or you have some kind of extra contrivance, something else comes through with. And the idea is that you will cancel off the ADS vacuum to 50 decimal places, and then you will appeal to the anthropic principle or the misanthropic principle and say, well, the reason the universe is as it is, we've got some magical cancellation and human life exists, and we are here to give talks about string phenomenology. And to me, I just don't think this is true. I don't think this is kind of probably the correct way to think about it. So my feeling is that the ADS vacuum are in some sense natural. They're really there as part of the theory. And while I understand how to solve the cosmological constant no better than anyone else does, I do think that this sort of contrived cancellation that is kind of common is not going to be on the royal road to the true theory of everything. So this talk is about focusing and studying and trying to understand the ADS vacua, which I think are kind of natural in string theory and natural in moduli stabilization, and that have still lots of interesting properties. And if we weren't thinking about the cosmological constant, we would be very happy to use as a basis for particle physics model building. And hopefully by understanding the ADS vacua, we can get some of the more deeper structure, which will enlighten us on as to what ultimately the true story is. Okay, I'm going to talk about two examples of moduli stabilization. So one is LVS and another is the type 2A DGKT flux vacua. Why am I going to focus on these two particularly? It's the thing that is interesting about both of these, certainly interesting for the purpose of what I'm saying, is that these can give you vacua at the asymptotic regions of moduli space. So these can give you vacua which are at quote unquote approximately infinite volume. They are very, very far away from the center of moduli space where all the volumes are one, all the couplings are one. So in LVS, this arises that you've got an interplay of alpha prime and non-perturbative effects, and suddenly these surprisingly come together to give you a non-supersymmetric ADS vacuum, which is basically exponential large values of the volume, which goes as e to the kind of constant over G string. Fluxes can put G string small, so you can make this volume basically as large as you like. With DGKT, you've got flux stabilization in 2A, and by going to larger flux quantized numbers, you can again go to large volumes and scale separation.
Joe, can I ask you a dumb question? Sorry.
Go ahead. Yep, those questions are dangerous, but go ahead.
So the classical limit is infinite volume. If I think of
GS, the classical limit, what do you mean?
Thinking of GS as H bar, I take that to 0, so I get infinite volume.
So in the LVS, all other things being the same, GS going to 0 will put you will make the volume of the volume large. Yes, infinitely large. Yeah.
Okay. Okay. Let me let you keep going. I got to
press. Okay, we have to be careful because it's not giving you 10D flat space. But yeah, let me.
Yeah. Sorry.
Yeah. Okay, so in LVS, it's easy to kind of put parameters in where you could get volumes that are kind of 10 to the 50 or 10 to the 100 in string units. And the reason this is nice is that it gives you hierarchies and it gives you parametric decoupling of modes. So you've got a very good scale separation between where the moduli are, say, where the KK modes are, for example. So you've got a clearly defined notion of what are the light fields, the light modes, and the heavy ones. And the decoupling you can associate to a clear geometric region, which is that the volume's getting really, really large. And this is your kind of parameter, or 1 over the volume is your parameter that is giving you decoupling. So here is just more for reference than something else. So in LVS, when you look at what happens to the moduli, the complex structure moduli are flux stabilized. They are effectively heavy. The small Kähler moduli, when you have this sort of Swiss cheese picture, they become heavy. And the ones which are light, or at least have masses not larger than the inverse of the ADS radius, are just the volume modulus and its corresponding axiom. So this is in a minimal LVS scenario. These are your light fields, and this is your effective Lagrangian in ADS space that describes the dynamics of these fields once you integrate out all the heavy fields. And given this effective Lagrangian, you can solve for the minimum of the potential and expand about it and determine masses and coupling in the ADS minimum. DGKT, this is another well-studied model. This is in contrast to 2B, so it's not using the GKP no scale structure as a starting point. It's using fluxes from the get-go. Because in 2A you've got like 2 cycles, 3 cycles, and 4 cycles, and you can put fluxes in all of them. You could do fluxes to stabilize everything. And there are certain limits of this where you can get to large volumes and have scale separation. So again, you have a potential and you have an effective action. The effective action and Lagrangian here is shown more for the purpose of just emphasizing that it exists and you can calculate with it rather than for the purpose of for you to remember it. Right, okay, so as I said, the purpose of this talk is to look at this such vacua holographically. And the reason for doing this is perhaps a holographic approach, given you're in ADS space, this is not a hugely explored topic. And this may reveal interesting structure, or that's opaque in traditional treatments, or inconsistencies that are opaque in traditional treatments, which would be nice, because it would be nice to rule out large classes of vacua if there was some hidden inconsistency there, and say that, LVS or KKLT or DJKT or anything just could not possibly be correct, because then it would narrow down the space of theories we would be looking for. So we want to say, if these things are there as 4-dimensional ADS vacua, then it should make sense to talk about them in the language of 3-dimensional conformal field theory. And in this map from ADS vacua to 3-dimensional conformal field theory, the scalar fields in the ADS space, the moduli, will turn into operators, scalar operators for the case of scalar fields, will turn into operators in a 3-dimensional conformal field theory. These operators will have certain conformal dimensions, and these conformal dimensions are related to the masses of the moduli by the relation here, which for a 3-dimensional CFT going on to 4-dimensional ADS is that delta on delta minus 3 is the mass squared times the ADS radius squared. So the right-hand side is something you can just compute in your ADS minimum, and then turn this into a value for delta. And it's useful, I think, when thinking about these things, to think about scales. So there are 3 basic, in a limit where you've got genuine scale separation, there are 3 possibilities, really, that you have fields which become parametrically heavy, much heavier than the inverse ADS radius. You have fields which are parametrically light, much lighter, masses much lighter than the inverse ADS radius, and you have fields which are comparable to the inverse ADS radius, which I've called interesting. And the reason for this is that in this limit where you're approaching the asymptotic boundaries of moduli space, then the heavy fields, the conformal dimensions zoom off to infinity, so you sort of forget about them in some level when you're focusing just on the low-lying dimension operators. The light ones, the conformal dimensions all go to 3, because the mass is going to 0, so the dimension goes to 3. So that's also, those also simplify. And the other ones, maybe the more interesting ones, will go to kind of, order 1 values, somewhere between 3 and 10. At least if their masses are positive. If their masses are tachyonic, they can be below 3. Right, so in LVS, almost all the stuff are heavy. Almost everything decouples. And the stuff that is light is really only or interesting is only really the overall volume modulus and the volume axion, and also the graviton if you are including gravity as a dynamical field. And then this then gives you, this is work I did with Fernando a couple of years ago. This gives you a quite interesting thing that in the limit where the volumes go really, really large, then your conformal dimensions all actually turn out to be fixed. They don't depend on the fluxes. And LVS, sort of turns in, from a CFT point of view, turns into one theory. How you would define this theory microscopically from a CFT side, I have no idea. But the properties of the conformal dimensions for the low-lying fields are completely fixed. So the volume modulus would end up at this unique conformal dimension in the CFT side of 3/2 on 1 plus square root of 19. The higher point operators also for the low-lying fields would also be fixed. And I just want to also emphasize also that when looking at this from an ADS side in this scale separated limit, the 10 to the 500 flux choices are all basically dropping down to there's basically, there's a single CFT and there are small perturbations about it. Okay, let me just pause briefly here for any questions before I move on. Okay, I will move on. Right, so with LVS, you can also look at the higher point interactions, and again with these, that when you expand about what the vacuum in the large volume limit, you find that all of these are fixed, all the flux dependence drops out, and everything is just nicely expressed in terms of the ADS scale. So you fundamentally, if you would turn this to the language of CFT, you have a unique form of interactions in the large volume limit, and then you would have subleading corrections, which would be suppressed as 1 over log volume. So I think probably in a CFT log of n, if you regard a CFT limit as a large n limit. Okay, so now move on to more recent stuff, which is the work done with Filippo and Siri. So this is looking at the DGKT flux vacua, which are in 2A. And so again, we ask the same question. We look at the limit where you take the limit of DGKT, where the fluxes are scaled so that the volume becomes really, really large and you have scale separation. And then we say, well, to consider the ADS vacuum, what are properties of this viewed in from a holographic point of view? And so again, you first of all have this shrinking of a landscape to really, in some sense, a sort of almost a single theory, or a single theory modular a couple of discrete choices, which is that the conformal dimensions are all reducing to single values, and they're dropping their dependence on fluxes. Same with the 3-point functions. So the landscape is again disappearing. But something else interesting and quite striking and unexpected is happening with DGKT. This is that the conformal dimensions are turning out to be integers. So in this large limit of large fluxes, where you take you're going to basically pushing DGKT into the limit where the volume becomes really large, so all the kind of higher order effects, subleading effects, should all drop out or be parametrically suppressed. And so then the conformal dimensions for the Saxion sector. So there's the Kähler moduli and there's the Kähler axions. So the Saxion sector, the Kähler moduli. So these dimensions all go to be end up as fixed integer values. So 10, 6, 6, 6 in sort of the minimal 2A model that's described, the simplest 2A model described in the DGKT paper. And the axions also take on integral values. So the exact mass things that actually depends on the signs of the fluxes. So the signs of the fluxes affect whether the vacuum is supersymmetric, but they don't affect whether the vacuum exists. In perhaps the most SUSY case, which is maybe the best defined ones, the axions are then 11, 5, 5, 5. But even in the non-SUSY case, the axion ones are still integer, and then either 8, 8, 8, 2 or 8, 8, 8, 1. The choice between 2 or 1 is because if you go back to this expression for the conformal dimensions, so if your mass is negative, you see there are 2 possible solutions for the value of delta. And so because there are two possible solutions, it could take either value. So there are 2 solutions consistent with that equation. when you've got a tachyonic field consistent with the Brighton-Loner-Friedman bound. But the thing that is rather striking and was completely unexpected is that these dimensions are all integer, because this is a hidden structure, and it's a hidden structure that is not kind of directly apparent from the the original formulation of DGKT. Okay, so there's so the things I want to kind of say about this is that it's a unique. First of all, it's a unique form. So yeah, in contrast to this picture of the landscape, so the landscape picture is that you have loads and loads of flux choices, and every flux choice gives you a different low energy theory. Whereas this is rather different in a way. So this is in some sense, when you're having vacua in the asymptotic region, and instead of having a landscape of theories, on some level you have one theory. That viewed from a CFT perspective, if you're looking at how the operators and the low-lying operators of the CFT behave, there's only really one theory. The dimensions are fixed. They just have integer values. They don't depend on the fluxes at all. The same with the higher point interactions. So the landscape here has basically disappeared, or in that it's present, it's into the sort of the spectrum of the very high dimension operators, which are in some sense the kind of least interesting ones, the ones associated to the KK modes. The other interesting thing, which I don't understand at all, is that the conformal dimensions are integers, because this is definitely structure. It's from a CFT thing. This is definitely these are not random numbers. I mean, in LVS you had this 3/2 and 1 plus square root 19, which is also a number, but it's not quite as as integers. But in this case, and the integers are coming from diagonalizing a 4x4 matrix. So there's not a 4x4 mass matrix. So it's not that there's an obvious cause as to why they should be integers. And also, if I just come back to the expression for the conformal dimensions, remember, this expression is quadratic. It's quadratic in the conformal dimensions, so it's not like the masses necessarily have It's not that the masses have the ones that are necessarily a simple form. It's there's no that this quadratic equation in delta should have integer solutions. Does not seem to me at all obvious. Yeah. Okay. So this is something that basically I think is interesting, but I don't understand it. Okay, so then I want to sort of come on to them. Let's just make some more speculative comments here. Okay, so one of the things is like how many vacua can you get in string theory that are really kind of like asymptotic and scale separated? And there aren't that many examples. The modular stabilization literature, there aren't that many. I think LVS is one. I think DGKT is one. I don't think there are many. I mean, if you look at things like ADS5 cross S5, which is you can dial stuff up to arbitrary large volumes. It's not scale separated because the curvature scale of the S5 is the same as the radius of is raised to the radius of ADS space, so they don't scale separate. KKLT I don't regard as scale separated because the volume is logarithmic in W0. So the thing you can try and get small in KKLT is W0, but then the actual kind of volume of the extra dimensions tends to be logarithmic in W0. So you don't get, I don't think in KKLT you get a real asymptotic regions of moduli space in the way that you do here. I mean, and I should note these are both going to asymptotic regions of Kähler moduli space, where you're going to very large values of the volume. In principle, there could also be stuff where you're going to very large values of the string coupling, or you're asymptotically large values of the string coupling, or at asymptotically points in complex structure moduli space. So there was this attempt by Thomas and Irene to look at with flux vacua the structure of the potential at asymptotic regions of moduli space. So there, I mean, what they have there in terms of the behavior which gives you a vacuum is something that reduces to the 2AK, so basically reduces to DGKT. So I think it's kind of it's an interesting question in itself. What examples are there of vacua that are really kind of in string pheno that are kind of asymptotic and scale separated? And just although this talk is slightly on the more formal side of the subject, I should say another reason I think it's important to look for such vacua is nature is defined by small numbers, and those small numbers must have an origin. And if you're serious about string theory, though, we think those small numbers should be coming from properties of the string vacuum. So you need a way of having small numbers. So the small numbers in nature, so you have the Yukawa couplings, the gauge couplings are all certainly deep in the perturbative regime. You have the scale of density perturbations, which is also small. So yeah, there's lots of small numbers in nature, and we need an origin for them, and the hierarchy problem as well, obviously.
So 4 minutes.
Fine, yeah. Is whether this, so from a CFT side, I already said that so LVS goes to kind of fixed values of conformal dimensions for the low-lying fields in this limit. DJKT does the same, where they'll integer. Is this any way to argue this from a CFT point of view? I mean, so for a landscape, we talk about 10 to the 500 fluxes, but from a CFT side, this is almost looking like isolated theories, almost like isolated points in the moduli space of things which are both scale separated, and what are the conformal dimensions of low-lying operators, or low-lying single trace primary operators. So whether there's any way this could be argued from a CFT side, that there is really only there's possibly only a very small number or a unique set of properties of theories which have scale separation and hierarchies. And then this other question, which is again is mysterious, is where these integer conformal dimensions are coming from DGKT. So I just want to point out, so all this is approaching this from the ADS side, saying we have an ADS vacuum, and then this would correspond on a CFT side to a theory which has these conformal dimensions and these interactions. None of this is a microscopic construction of a CFT theory. So obviously, if a CFT of a three-dimensional CFTs could be found with such properties, it would be extremely interesting, because I think this is definitely a big open question in the subject. If ADS vacua exist, what are their CFT joules? Okay, so let me get conclusions. There's been a lot of work on modular stabilization. There has been nowhere near as much work on looking at them from a holographic side, but I think this is an interesting and worthwhile thing to do, because it provides a new perspective on old problems by reframing the old established constructions in a CFT language. It both reveals structure that I think is not kind of appreciated before. So, for example, these integer conformal dimensions in DGKT, I don't think this structure was kind of realized before. What it means, I don't know, but it is kind of structure there in the theory that I think is not apparent in the standard way of formulating it. Likewise with LVS, I think this fixed conformal dimension, again, it's something which is not really apparent before you look at it from a CFT point of view. Where this structure comes from, I don't know, but I think there are lots of interesting questions to be asked about this. And then the big kind of question here ultimately is, by looking at these from a CFT point of view, can this be used to establish the consistency or the inconsistency of such kind of structures of modular stabilization and the low energy Lagrangians that they give rise to? Okay, so while having coffee prepared this, I have, if you can see on my screen, I've got, some of you may remember, this is String Pheno, from the String Pheno Conference 2004 at the Michigan Center for Theoretical Physics. So String Pheno has been going a long time, and I hope to be having another mug from the 2044 String Pheno meeting. Thank you.
Okay, thank you, Joe. Other questions? So while we are waiting for the questions, maybe I ask one, which is, so how much should we read into this integer conformal dimensions? You mentioned LBS does not have this feature, and DGKT has. And there has been a class of three-dimensional ADS vacua that was claimed to also have the scale separation property. And this is compactifying type 2A on G2, something that Thomas Van Riet and collaborators have done a couple of years ago. I wonder if you have checked, or you know whether this case would fall into the integer type or the non-integer type. So
my understanding from Fee Napers, who's just started working with me as a PhD student and has just actually moved from Thomas's group where she did a master's, is that doesn't have integer.
Okay.
Dimensions, but yeah, it isn't something I've yet studied myself, so I don't have any deep thoughts on.
Mm-hmm. So it could be a peculiarity with DGKT itself.
It could be. I mean, there's also things that CFT in 2 dimensions is different from CFT in 3 dimensions. Okay. Yeah, I mean, it's something. The thing is, I really don't know why the integers are there. I just have no actual understanding, like deeper understanding of why they are there. So this is why to say why. I mean, okay, LVS is non-perturbed. There's non-perturbative structure, so it's a different type. LVS is genuinely a different type of construction to DGKT. The 2A going to 3D is maybe more similar, but I don't have any. To me, it's a puzzle. It's just odd that they're integers.
Right. Thank you. So there are two questions. The first is from Fernando and then Florent. Fernando, maybe you can go first.
Okay, great talk, Joe. Very nice. So just a couple of comments you mentioned at the end. The fact that you say that the KKLT you don't consider a scale separated. I understand. I mean, the volume is not that large, and you can see that the string scale and the Kaluza-Klein scale may not that be different. But for instance, the gravitino mass and so there is a hierarchy because of the W0 dependence. Don't you think that there's
So maybe let me put it this way. Okay, so with LVS, there's a kind of a way, you've got an exponential way of basically sending the volume off to be as large as you like. With DJKT, you can just dial the fluxes and make them as large as you like. With KKLT, the equivalence would be basically making W0 as small as you like. And okay, so you know that in the sort of the traditional way of doing that just through fluxes, that's extremely hard because you have a quadratic scaling and you just sort of run it off. Then there's this more modern recent way which is doing basically like Liam's group is on using like basically racetrack on the racetrack and instanton corrections on the dilaton, I think. Which is to get that, but then basically it's like so then you're getting you're getting small W0 is you're getting small using a racetrack, and racetrack doesn't take you. In my view, racetrack is not something you can just scale something. Yeah, something you stabilize with your racetrack. In my view, is not something you can take off to be just as small as you possibly like. You're always looking at basically a discrete construction. When I've heard Liam talk, the things that we over 1 over 252 over 1 over 253, and you need something to kind of set up in that way. You cannot just turn that to 1 over 10 to the 6 and 1 over 10 to the 6 plus 1, for example. This is why, to my view, I don't regard, KKLT as really having something you can just take off to be deep in the acid.
And the other comment you made that LVS looks very arbitrary from the flux point of view, but from the CFT side, you say it's almost isolated. Could you expand a little bit on that?
So often the people would make these talks and say there's a landscape. Maybe people not string theorists make these talks, but anyway, there's 10 to the 500 fluxes, and every one of these flux choices gives you a different low energy Lagrangian for the theory. So you can never predict anything because any construction you get, you just pick another one of these 10 to the 500 flux choices, and your theory will just be totally different. But so this is saying that then when you look at this as a theory, from the ADS side, the properties of this thing as an ADS minimum are basically isolated in CFT space. That there's a sort of there's particular values for the conformal dimension, and you have you maybe have small corrections about that. But basically, these theories are concentrated at a single point in CFT space. So it's not the case that by making however many arbitrary flux choices, you can just change the theory to whatever you like.
So in some sense, you're thinking that the mapping is you see many ADS solutions, you would have the CFT will capture all of them at the same time.
Yes. And no, this is a property of being in ADS with the standard constructions. Coming back to what I said at the start, if you throw in some arbitrary de Sitter uplift, you lose all of this.
You lose it. Very good. Okay, thank you.
Okay, so next is Florent and then Alexander.
Hi, thanks for the nice talk. You find integer conformal dimensions, but do you expect higher corrections to give them an anomalous dimension, or do you expect them to always be integers?
Okay, so I see no reason why. Okay, so presumably there's some structure that gives you integers, but I don't see any reason why the structure should be preserved against 1 over n corrections. So normally in CFT you would expect there to be anomalous dimensions, which are order 1 over n or 1 over n squared, and these would move things away. So I don't see any reason why these should be protected from such higher corrections, but they will be in a CFT language. They will be 1 over n corrections. So if you're in the asymptotic region where n becomes extremely large, 1 over n can be extremely small.
Okay, so I should understand them as like short multiplets that get an anomalous dimension. At least in the SUSY case.
Yeah, because I mean, so this is n equals 1 SUSY. So there were, I think, there would be no reason that they would be like,
Okay,
yeah, be BPS protected or anything. Yeah.
thanks.
Okay. So we have two more questions. First, Alexander, the Lord of Darkness.
Okay, I have to do this again. I feel like in a police department being interrogated when I put the land like this. Hi, Joe. Thanks a lot.
Hi.
Very interesting. Now I don't know. So I have a bunch of connected questions. So how many am I allowed to ask before I start? You know, because I may have to prioritize. This is where I'm asking. I mean, like, the first one is maybe a quick one. I mean, like you talk about asymptotic vacua. I mean, if I understand this correctly, and for LVS, for instance, I mean, the volume goes like e to the exponential of 1 over GS if you want. You would need to send GS to 0, which you have to do via flux choices. And as far as I know, we have increasing evidence that the number of flux vacua we have in type 2B is finite. We cannot just, you know, we cannot literally send these things to infinity. And you could argue for any finite maximal value of the volume you can then get, the actual asymptotic region is outside.
Yeah, I mean, so okay, so this is.
I would just say these different three classes like KKLT, LVS, DGKT, they are at various level of how interior they are. And then KKT is more interior. I agree with that. But I mean, you're not strictly asymptotic, right?
Yeah, I mean, so this is kind of a physicist sense in which 10 to the 200 is approximately infinity. Of course, a mathematician will shoot you.
I agree. No, then I understand how you mean it. I mean, how you use the term. No, the other thing is what is connected to me is the following. I mean, there is this hope, of course, you get these CFT operator dimensions, and then you know the long-term hope maybe that people like with a conformal bootstrap or whatever could basically show that some of these spectra are like forbidden, that cannot exist as a consistent quantum CFT if you want, right? And then you could kill the whole branch of vacua or something like that. But what I don't know is the following. Imagine you move in from infinite volume where you get these operator dimensions. Don't the dimensions change when you go to finite volume? Shouldn't they have volume dependent corrections like that? The dimensions are changing. I mean, like you get your theory literally at infinity, right?
Yeah, but okay, so there's two. I mean, this I don't regard as such a big thing because
I'm just asking. I mean, how much do they change? Do they change it? I mean, I'm just
yeah, they change. So in LVS they would change as basically one over log volume.
1 over log volume.
And so we did look at this numerically.
But,
so the thing is, so if you're at volumes of like say 10 to the 15 or 10 to the 20 or something, you know, the way in which the distance the amount you're away from the asymptotic values is about 0.01. So your asymptotic value is say 8.04, and your actual value is about 8.03.
Exactly, but what I'm asking is the following. I mean, I remember when people do conformal bootstrap and find this Ising critical point and these kind of things, they can actually compute. I mean, and the boundary can be quite sharp. So what I'm wondering is, could it happen that, for instance, you know, we don't know this yet, of course, but that you rule out the actual asymptotic spectra or an asymptotic spectrum, basically, at literally infinite volume. But when you move in, the dimensions change such that they become viable from a future, you know, rule out bootstrap like rule out argument, and therefore they would establish you not that the branch is wrong, but you get an upper bound on the volume. You get kind of that you have to find the finite landscape back.
Yeah, no, that would be yeah. So I mean that would be that would be interesting. And Filippo and I in our first paper we had something interesting where the sign of the anomalous dimension. So in LVS we have this thing about 8.04. And the sign of the anomalous dimension for a certain group of operators changes if this would go below 8. And as you move in, it does change from like 8.04, you know, and it goes down to like say 7.95 when the volume is 1,000 or something. And so there is something physically interesting which changes sign as you move in. So yeah, in principle, possibly there is something that could go in that direction. Yeah.
Is the sign definite or just from examples?
The sign is so you can compute the sign for the so in LVS it's quite interesting because there's basically a fixed sign for the anomalous dimensions and it also ties up to lots of other physical things. So if the sign is wrong, the theory is kind of if you flicked the sign in the Lagrangian, you would clearly put the theory in the Swampland because it does things like, for example, sends the axion decay constant to infinity rather than 0 as you approach the decompactification limit. But in some other examples, we didn't see the same behavior, so I don't know whether that actually means means
Right.
anything. Just in LVS, the sign of the anomalous dimension does tie to sort of physical behavior. Yeah.
Right. So also in some of the studies of very large black holes in ADS, I think one can also tie the sign of the anomalous dimensions to, say, unitarity causality conditions. But okay. Federico, he has been patient.
Hello, very nice talk. So I wanted to make a comment. If we look at the representation theory of 3D n equal 1 superconformal algebra, we have that multiplets are one-sided, so we can put one shortening condition, but just one. And looking at the possible shortening condition, we find that only long multiplets can have integer dimension. So if you say that all the operators that you have integer dimension, this is a CFT that has no short multiplets at all. So do you know what, I mean, it's very, very peculiar, I would say. Do you know what this can tell us?
So, okay, so the statement you've just made is completely new to me. So
yeah, it's just like looking at the tables in Cordova-Dumitrescu, they classify all the possible multiplets for all the superconformal algebras in all dimensions. You can look at 3D n equal to 1, there are only long multiplets with integer dimension.
yeah, I don't, it's not something, yeah, I just, this is the first time I've heard that statement. So I think maybe I would try and, ask you offline, because I don't have any comments about it because I haven't heard it or thought about it.
Yeah, I just thought it was a very,
that's interesting.
it's a very, very peculiar feature for 3D n equal to 1 SCFT, I would say.